Thank you very much for coming to this talk, which is entitled Coextensive Varieties via Central Elements. Some preliminary first on the theory of central elements. So in this work, we will we are dealing with varieties with at least a constant symbol. So we say that a variety with 0 and 1 is a variety with the zero terms 0i and 1i, with 1 smaller than I smaller than n, such that this quasi-equation here holds. If A is an algebraic variety, then we say that an tuple of A is a central element of A if there exists an isomorphism from A into the direct product of two algebras, such that every component of E is centered in the pair composed by 0i and 1i. And similarly, we say that a pair of n-tuples of A are a pair of complementary central elements of A if there exists an isomorphism from A into a direct product of two algebras, such that it does the same with respect to the n-tuple E, and it sends or it maps every component of F in the pair composed by 1i and 0i. So a pair of congruences, theta and delta of an algebra A is a pair of complementary factor congruences if their intersection gives the diagonal and their composition gives the top of the lattice of congruences of the algebra. So here's a main theorem, which was proved by Johnny and Sanchez-Terraz, and says that if V is a variety with 0 and 1, then the determining property, which means that every pair of complementary central elements determines a unique of complementary factor congruences in this way, this is equivalent to say that V has Boolean factor congruences, which means that the set of factor congruences of any algebra in V is a Boolean sublattice of its congruence lattice. Finally, this is equivalent to say that V has definable factor congruences, which means that there is a first order formula that defines the left kernel in direct product composition by means of these conditions expressed here. Now, if we have a variety with 0 and 1, which has V of C, then we write Z of A to denote the set of central elements. The symbol here denotes that E and F are complementary central elements of A. We say that E is a central element of A, and if E is a central element of A, then we write in this way the unique part of complementary factor congruences satisfying these conditions in here. And the important thing about all this is that in this context, in varieties with VFC, then we can establish a bijection between the sets of central elements of A and the set of factor congruences of A, which at its time it allows us to endow the set of central elements with a Boolean algebra structure that gives us an algebra which is isomorphic to the Boolean algebra of factor congruences of A. The interesting thing here is that this allows us to reduce the problem of studying congruences in terms of elements. So if we have a variety with VFC, then we say that the variety is stable by complements if every homomorphism preserves the relation of being complementary central element. It is important to recall that there are varieties with VFC with homomorphisms such that preserve central elements but does not preserve complementary central elements, and even are varieties with VFC such that their homomorphism does not preserve nor central elements nor complementary central elements. So for the first case, we can take the variety of bounded joint semilattices, in which this formula here allows us to prove that it is a variety with VFC. So if we take A as the product of 2 times 2, where 2 denotes the two-elemented bounded joint semilattice, it is clear that their central elements of the algebra is the elements of the algebra itself. And if we consider this homomorphism alpha, this endomorphism, it is clear that alpha preserves central elements but does not preserve complementary central elements. The second condition, we can take the variety of bounded lattices. It is well known that M has B and C, but if we take C as this 2 times 2 bounded lattice, and we take D as this 5-elemented bounded lattice, it is clear that C is a subalgebra of D, but due to D has 5 elements, it is directly indecomposable, so the inclusion does not preserve nor central elements nor complementary central elements. So it is a sensitive concept in the theory of central elements in general. So with this in mind, we can now start to talking about coextensive varieties. So a category with finite product C is called coextensive if for each pair of objects in the category, the canonical function times is an equivalence. Samples are abundant. For instance, we have rakes, commutative rakes with unit, bounded distributed lattices, the residuated lattices. Another concept which is important in this work is the notion of Pierce variety. So variety is a Pierce variety if there exists a positive natural number n and zero terms 0, 1 to 0 to 0n, 1, 1 and 1n, and a term in these variables such that the following identities hold in V. Examples of Pierce varieties are rakes and rakes with unit, here's the term, bounded lattices, and Church varieties, which are varieties with a ternary term and a zero terms 0 and 1, satisfying these equations in here. And as example of Church varieties, we can consider Boolean algebras, integral, bounded, and commutative reciprocated lattices. So the main theorem says that if we take a variety, the variety is coextensive if and only if V is a Pierce variety in which the relation of being a pair of complementary central elements is equationally definable. That's equivalent to say that V is a Pierce variety in which the class of directly indecomposable members in the variety is a universal class. And that's equivalent to say that V is a Pierce variety stable by complements. As a corollary, we obtain that V is a Pierce variety if V is a Pierce variety such that the subalgebras of subdirectly irreducible members of V are directly indecomposable. Then, if V is locally finite, then V is coextensive. And if V is a variety of finite types such that this condition here holds, then V is a Pierce variety if and only if V is coextensive. Another important notion here is the concept of variety of shells. Variety of shells is a variety in which there's a positive number n and zero terms written in this way and terms times I and plus I, such that this equation here holds. And if we have a congruous permutable variety of finite types such that the class of directly indecomposable members in the variety is a universal class, then it's equivalent that V is a variety of shells. That's equivalent to V is a variety with 0 and 1. That's equivalent also to V is a Pierce variety. And finally, it is equivalent to V is a coextensive variety. Finally, on some applications, then we need to recall that discriminator algebra is a non-trivial algebra A for which there exists a ternary term in the language, so that for every A, B, and C in the algebra in set, underlying set, these conditions here hold. And so a discriminator variety is a variety generated by a class of similar algebras, which are discriminator algebras with respect to the same term T. A particular family of discriminator algebras is given by preprimal varieties, which are generated, varieties generated by primal algebras. And an algebra is primal if it's finite, and every finitary operation is term operation. Canonical example of this are Boolean algebras. So, particular, we obtain that every discriminator variety with 0 and 1 is coextensive, and of course, in particular, every primal variety with 0 and 1 is coextensive. Well, thank you very much for your attention. Here are the references, and thank you